In this video, we are discussing resistors in series and parallel connections. So we have this set of resistors in series connection, so they're connected end to end. And then we have these resistors in parallel connection and they're connected side by side. That's another way of saying parallel connection, and that other way, end to end, is another way of saying series connection of resistors. Now we want to see how to add up these combinations. So the effective resistance of this particular connection, that is, these resistors in series, are just the equivalent resistance of the total thing is equal to, we just add up normally. So we have 4 plus 2 plus 5, that is all equal to 11 ohms. So that is the total or effective or equivalent resistance of these particular connections. Now, these are the same resistors connected in parallel, side by side. Now, for us to find the required resistance, so we do reciprocal addition. So we have 1 over the required 1 over the equivalent resistance is equal to 1 over 4 plus 1 over 2 plus 1 over 5. So we do reciprocal addition for resistors in parallel. So their LCM is all equal to 20. So 4 into 20, that's 5 times 1, which is 5. 2 into 20, that's 10 times 1, which is 10. 5 into 20 is 4 times 1, which is 4. So we have 19 over 20. Remember, 1 over R equivalent is equal to 19 over 20. So for us to get the required effective resistance, all we have to do is to invert, or you say you cross multiply and then divide both sides by 20. So this gives us that R equivalent is equal to 20 over 19. So that's just the inverse of the whole thing, which is 1 point something ohms. So you solve that with the calculator. And then one other thing we notice is that whenever we solve for resistances like this in parallel, the effective or equivalent resistance is always less than the least of the resistances, and further examples that we'll be solving will help us to understand this better. Now in this, we are tasked to find the effective resistance of these combinations. So what do? Let's say this is the source of EMF. We trace this way, so we can see that these two are in parallel, while the whole set is in series, like this is in series with this parallel connection. So what we do is we first of all get the effective resistance of the parallel connections. So 1 over R parallel is equal to 1 over 10 plus 1 over 10, which is equal to its same denominator. So we have 1 plus 1 is equal to 2 over 10. Now remember, this is equal to 1 over the parallel resistances. So when we invert, we have that is equal to 10 over 2, which is equal to 5 ohms. So the parallel resistance is equivalent to 5 ohms. So that 5 ohms is in series with this 10 ohms. Therefore, the effective resistance is the equivalent or effective resistance is equal to this 10 ohms plus this parallel one, which is equivalent to 5, plus 10 are all equal to 25 ohms. Now, in solving this, we notice that when we had this parallel connection, the equivalent was half of the value of one of them. Now, that's a quick way of solving resistors in parallel. If both of the resistors are of equal values and they are connected in parallel, then their effective resistance is always equal to the value of one of the half of one of them. That is just it. If you solve it, every time you have equal resistances in parallel, their effective resistance is always equal to, just pick out the value of one of them, divide that into 2, and voila, you have your effective resistance for that parallel connections. But remember, they must be equal. If they are of different values, then you have to do this reciprocal addition as usual. Okay, moving on to the next one. Okay, so what's the effective resistance of this combination? From what we learned from the previous example, we have to first of all get the effective resistance of the parallel connections. And from what we can see, they are of equal resistances. Therefore, the effective resistance is just 1 ohm. That is, we pick out the value of 1, which is 2, divided by 2, we get that. You can as well go ahead, do the reciprocal addition of these two values of resistances, and then you still get 1 as the effective resistance. So from now on, when we see something as simple as this, we solve just with our minds so that we can just pick up the speed of solving resistances. Okay, so as we have that the effective resistance of the parallel combination, so we have that RP is equal to 1 ohm. Just make sure you go ahead and solve it each time until you get that confidence. But if this was a theory question you're solving, you have to show all working. So, okay. Therefore, this parallel combination is in series with this. So the total effective equivalence resistance is equal to 1 plus 2, which is equal to 1 plus 2 ohms, giving us 3 ohms. Okay, here we have rearranged those 2 ohms to look like something else. Now let's see how to go about it. So when we trace with our fingers from the source, we meet a junction here. And whenever you meet a junction, just know that those 2 arms are in parallel to each other. So these 2 ohms is in parallel to this pair of 2 ohms that are in series with each other. So we trace, that's just like how to recognize parallel connections. So when we trace, we meet a junction, which is a point where, if it's roads we are talking about, we have roads divided into 2 or more different roads. So we have this. So this is in parallel to this, and these 2 are in series. So now we have to resolve the series connections first, and then we now do parallel addition with these 2. So for series connection, we just know we have to add them up. So the series resistors are equal to 2 plus 2, which is 4 ohms. And then the effective resistances are in parallel. So these 2 ohms is in parallel with a total of 4 ohms here. We have 1 over R equivalent is equal to 1 over 2 plus 1 over 4. And the LCM is 4. Here we have 2 plus 1, which is 3 over 4. Remember, this 3 over 4 is equal to 1 over is the reciprocal value for this. So R equivalent is equal to, we now have 4 over 3, which is equal to 1.3333 ohms. So that is the equivalent resistances. Okay, let's have a different combination. And here, right here, we have a different combination of 3 2 ohms resistors. Okay, so for this, remember we said, how do we recognize series and parallel connections like this? So let's start tracing from the source. We trace from here, we get to a junction, right? And then from this junction, we see this route and we see this other route. Now we know that whenever we meet a junction, that they are now we now meet a parallel connection. So this route, whatever thing that is on this route is in parallel connection with whatever thing that is here. And then when we now trace, we see that these 2 ohms, that's all we have on this other arm. And then these 2 ohms is in series because, yes, it is bent at this point, but we didn't branch to anything. So these 2 ohms is in series with these 2 ohms. And this combination is in parallel connection with this because of the 2 junctions. So we can see that this particular circuit is actually the previous one we just solved. But now they were now shifted, they were now bent, like this other side was now bent to this way, and then the source was now, did you when we compared the two, we can see that they are still the same thing, but we now shifted the wires. Remember, this represents the connections, the wires. Okay, so meaning that we have to first of all resolve the series connection. So 4 ohms is in parallel with 2 ohms. So when we solve, we still arrive at the same answer. Now let's see another connection. Okay, here we now combine 4 2-ohm resistors in this way. So from what we can see, yes, I know you guessed right, we got this junction is in parallel with this junction, and these two are in series and these two are in series. So we have 4 ohms, we have 4 ohms. And what we've learned so far in this video is that when we have two equal resistances connected in parallel, that means the effective resistance is equal to the value of just one of them divided by 2. Now, a combination of, we have 4 ohms, right? So when we pick out 4 ohms and divide it into 2, we have that the effective resistance of this whole combination is equal to 2 ohms. So the equivalent resistance or the effective resistance is equal to 2 ohms. You can see that. But you could as well pause the video, go ahead and try it. You keep on doing this until you gain the confidence and the understanding of how to solve this quickly. Now, this is equivalent to 2 ohms. Let's say we now bridge this point. We now bridge. We have a wire here. So, you know this has changed. The whole thing has now changed. So, how do we go about solving this? We have to see, when we got here, we met a junction and we met another junction. So, these two are in parallel. Now, because of this bridge here, is no longer in series with this. So this bridge is just like a wire joining these two together. So we have two parallel connections, in which we have to solve them differently. Yeah, we have to solve them differently actually. So this parallel connection is in series with this parallel connection, because another way of drawing this is to have the parallel connections here, and we can now see something of this nature, and then we now have the resistance is this way. So this is another way of seeing it, that this parallel connection which represents this is in parallel to this, because this is just a wire. So we have that the effective resistance of this parallel set is equal to 1 ohm, and the effective resistance of this parallel set is equal to 1 ohm. So as they're in series with each other, we add them up to still get that the equivalent resistance is equal to 2 ohms. Now you will say, they were the same thing. This wire didn't change anything. Please, if you're to show all working, you have to understand the fact that this wire now made this side to be in parallel with to this side. So you have to, if you're showing all working, you have to still realign and then show the working. Okay, now we've invited a 3 ohm resistor, but the whole thing is that you should pause the video or just look at it and tell me what's the effective resistance. Can you see that with your eyes, even without solving? But just make sure you really know how to solve, like you can show all working correctly with all the steps complete. But before that, what's the effective resistance? 4 ohms, right? Because this combination is 1 ohm, right? And then plus 3, which is 4. So we can see how easy it is for us to solve resistors in series and parallel connections.